Lesson 9, Probability and Expectation. All right, we're going to start with a definition here of random variable. It's a real valued function defined on the sample space of an experiment. Recall the sample space is the set of all outcomes. And so the random variable is going to take on a single value for each outcome. We're going to start out with the discrete case here first. In a few lessons, we'll talk about the continuous situation. Discrete random variable takes on probability from a countable set. The term countable refers to a set that's either finite or has a specific size of infinity, which is basically equivalent to the size of the set of natural numbers. In this course, for the most part, the discrete random variables we work with, we're mostly going to be dealing with finite situations. Continuous random variables, that's a different setup. Probability mass function. So we have a couple of properties here to satisfy a PMF. The sum of all the probabilities, sum of all the values has to be 1 for 100%. And the probabilities are all positive. The expected value of a discrete random variable x that is the summation of each x value times its corresponding probability. So expected value of x is summation x times p of x. It's also the mean of the random variable x. All right, let's take a look at an example. We're rolling a single die. What's the expected value of the face value rolled? So here our random variable is going to be matching the face value of the roll. So the values of x are going to be 1 through 6, and the probability for each of them is the same, 1/6. So the expected value, we multiply each of the x values times its corresponding probability. In this case, all the probabilities are the same. So we have 1 times 1/6 plus 2 times a 6 plus 3 times a 6 all the way up to 6 times 1/6. Again, in this case here, 1/6 is constant. It can it's the same probability for each x value. We could factor that out. We get a common denominator there. It's 21/6, which is 3.5. So the expected value here for this random variable is 3.5. All right, second example. A coin is flipped 4 times. X is the number of tails flipped. Find the expected value of X. How many times do you expect to get tails if you flip a coin 4 times? So we're flipping a coin 4 times. There's 2 possibilities, HT for each flip. So the total number of possibilities is 2 to the 4th, which is 16. And these are the 16 outcomes listed here. So what are the possible values for X, the number of tails that are flipped? You could get 0, 1, 2, 3, or all 4. And we have the corresponding probabilities. Each of those strings of 4 flips has a probability 1 out of 16. So it's just a matter of counting how many ways there are to achieve each number of tails. There's only one way to get 0 tails. It's got to be 4 H's. So that probability is 1 out of 16. There are 4 ways to get 1 tail. The 1 tail can occur in each of the 4 slots. So that's 4 out of 16. For exactly 2 tails, it's 6. That's 4C2. We'll see this in a little bit more detail in an upcoming lesson. There are 4 ways to get exactly 2 tails. I suppose you could count this also with the permutation with the duplicates as well. It would be 4 factorial divided by 2 factorial, which is 24 over 4, which is 6. And then 3 tails, which would correspond to 1h. So that's 4 out of 16. And then all 4 tails, there's only one way to do that, 1 out of 16. All the probabilities are positive, and the sum has to add up to one whole. If you add those numerators up, you get 1, 5, 11, 15, 16. All right, so now we're going to calculate the expected value of x by doing the sum of each x value times its probability. So it's 0 times 1 over 16 plus 1 times 4 over 16 plus 2 times 6 over 16, and so on. And the end result here is 2, which should be reasonable since if it's a fair coin, there's a 50-50 chance. You're flipping 4 times. It's reasonable to think that you're going to get two H's and 2 T's. That doesn't mean it's going to happen that way, but in the long run, we expect the mean to be 2 out of 4 tails. Okay. All right, example 3. 2 cards are drawn from a 52 card deck without replacement. If they're both clubs, you win $10. If they're both red, you lose $7. Otherwise, you lose $2. Let X be the player's winnings. What's the expected value? So the X values here are the amounts that you can either win or lose. You could either win 10, lose 7, or lose 2. So those are the X values. Now we have to calculate the probability of those occurring. So how do you win $10? You have to get a club twice without replacement. The first draw, there's 13 possibilities for the first club. Then you want to get another club. There's only 12 left for the second one. Denominator, there's 52 total cards. The first draw, after removing one without replacement, goes down to 51. What's the probability of losing $7? You have to get both cards red. Half the cards are red, diamond and heart. So it's 26 for the first selection and then 25 for the second, over 52 times 51. Now, otherwise, you lose $2. Now, we could calculate that directly, but we know that in a probability mass function, the total has to be 1. So whatever's left over has to be the remaining probability, 1 minus the other values. So simplifying those probabilities a little bit, we get the probability of winning $10 is 156 over 2652. Losing $7 is 650 over 2652. And losing $2 is 1,846 over 2652. And then we use the formula for the expected value, summation x times p of x. So again, it's 10 times the fractional probability there, 156 over 2652. Then we have a negative 7 times 650 over 2652 and a negative 2 times 1846 over 2652. And that turns out to be approximately negative $2.52 per play. So on average, if you play this game many, many times, you would expect to lose an average of $2.52 per play. All right, little variation of the first example. We're rolling a die. X is the face value, but we're doing a slight extra calculation here. We're going to compute the expected value not of X, but of X plus 4. So we're finding the expected value of a slightly more complicated expression, X plus 4. So we have the original setup here. The values you can roll are 1 through 6. All the probabilities are 1/6. We're replacing the x now with x plus 4. So everything just shifts over. We add 4 to each x value. And then we compute the expected value of that expression, which is going to be each x plus 4 value times its probability. Now, all of those are 1/6. And so you get 45 over 6, which is 7.5, which is the same as the expected value of x first plus an additional 4. The original expected value here was 3.5. The new expected value of x plus 4 is 7.5. So we literally just ended up adding 4 to the original expected value. And that's not a coincidence. In general, here, if you're doing the expected value of x plus a constant, it will end up being the same thing as e of x plus the constant. A small proof here, if you want to calculate the expected value of x plus 4, it's the sum of x plus 4 times each probability of x. Distributing the p of x through, we get summation x times p of x plus 4 times p of x. We can do those sums individually. We get the sum of x times p of x plus 4 times the sum of p of x. The sum of x times p of x, that's just the expected value. That's the mean. That's e of x. We have a probability mass function here. So the sum of the probabilities is 1 whole, and we're left with e of x plus 4 times 1, which is e of x plus 4, which is what we got here. And so in general, if you have expected value of a constant times x plus another constant, expected value of ax plus b, we can rewrite that as a times the expected value of x plus b. All right, CDF, the cumulative distribution function of a discrete random variable. So we're using capital F to denote the cumulative distribution function, and it's equal to the capital F of x is the probability that x is less than or equal to x. So it's a running total of all the probabilities less than or equal to the input value. Let's take a look at an example. If we flip a coin twice and x is the number of tails, we have the following PMF. So what are the possibilities here? We can get HH, HT, TH, TT. The outcome HH has 0 tails in it, so x would be 0 at that outcome. The outcome HT, there's 1 tail. TH is 1 tail, and TT would be 2 tails. Each of those outcomes is equally likely, 1/4 for a fair coin. So the probability of a 0 is 1 out of 4. The probability of 1 tail is 2/4 or 1/2. And the probability of 2 tails is 1/4. So that's our probability mass function. To find the cumulative distribution function, we do the running total. So f of 0 is 1/4. F of 1 is going to be 1/4 plus 1/2. It's the running total of everything up to and including 1. So it's 1/4 plus a half, which is 3/4. F of 2, we're going to add up everything less than or equal to 2, adding up 1/4, a half, and 1/4, we get 1 whole. Now, this capital F is defined for all real numbers. So what's going to happen is if you pick a value in between 0 and 1, like f of 0.7, we're counting everything up to and including 0.7. So we'd just still be at a quarter. So it would stay level until we hit the next value that had a positive probability. So we'd have a jump at 1 and then a jump at 2. So summarizing this in a piecewise function, for anything lower than 0, the probability is 0. It's impossible to have less than 0 tails. So that is 0. Then when we hit 1, then when we hit 0, the probability was a quarter, and then it stays that way. It stays that way until we hit 1, when it jumped up to 3/4. Because at 1, the probability of 1 was a half, so we had that jump there. So capital F of 1 was 3/4. It's going to stay that way until we get to 2 and the next jump of another quarter, which got us to 1. And then from there on out, we're at 100% and it stays flat. So this is piecewise function for the cumulative distribution function capital F. Again, it's a running total. Probability that x is less than or equal to x. So it's current probability and all the previous. And here is a graph of the situation. So for anything less than 0, the probability is 0. So the graph is horizontal on the x-axis that's a height of 0. Then when we get to 0, the probability of that happening was 1/4. The probability that x equals 0 is 1/4. So we get a jump in the graph there to 1/4. Then it stays flat here because the probability does not change again until we hit the 1. So it stays level there, constant at 1/4. And then at 1, it jumped up to 3/4. And then it stays that way. So it's again another horizontal segment there until we get to the 2. And then it jumped up to 1. Once we get to 1, that's one whole 100%. It's going to stay, probability can't exceed that. So for anything larger, it's going to stay at 1. So that is the graph of the CDF. The CDF is the cumulative distribution function. All right, this concludes lesson 9. As always, please don't hesitate to reach out via email if you have any questions. Thank you.